Hi everyone and welcome to Activity 11. Today we are going to talk about writing equations of our polynomials as well as finding some of the zeros. So when we are given a graph of our polynomial function, there are some things that we want to look at to be considered to include in our equation of it. Where are our x-intercepts, aka those zeros that we see on the graph, and are there any multiplicities? Do we notice any bounces at those zeros, aka maxes or mins, or are there any inflection points when they're passing through? Because that'll affect the degree at that particular x-intercept. We also want to consider the y-intercept of our graph because that can help us figure out if there is what our leading coefficient should be. So for example, we see in number 1 that we have zeros at a couple of places. There is one at x equals -1, and there is one at x equals 4. So when we put this into our factored format, we know that there is a 0 at x equals -1, so in factored form, that would look like x plus 1. A 0 at positive form means that in factored form, it looks like x minus 4. The other thing we are noticing then is that at that 0 at 4, there is a bounce, right? We have that multiplicity happening, and it's bouncing back and staying on the negative side of the x-axis. So we know that we would say that that is a squared, at least, multiplicity. And that makes sense because we have 2 turning points, so the degree is going to be at least 3 of this polynomial. Now, the last thing we want to consider is what is this leading coefficient out here? We know it's going to be negative because our end behavior, as our x's are going to positive infinity, is negative, but we want to know specifically what is it. Now, we can find that value of a by plugging in our y-intercept, that is at -8, because when our x value is 0, we know it's coming out to be -8. So if we solve this little equation, 0 plus 1 is 1, 0 minus 4 is -4, but -4 squared is positive 16. And then we can solve by dividing this 16 over, and we find out that our a value is -1/2. So when we write the final equation here, we want to include that leading coefficient of -1/2, x plus 1, x minus 4, quantity squared. On the second graph, this time we have 2 x-intercepts. One of them is at -4, the other is at +2. And again, as we plug this in, we notice that when you put it into factored form, again, kind of looks like the sign is flip-flopping from what it is at the actual 0. And both of these, this time, have a bounce back, so both of them will have a multiplicity of at least 2, in this case, an even multiplicity because we're bouncing back. And again, that makes sense because a degree 4 polynomial would have these 3 turning points, and we see that same end behavior. Now again, if we want to this time solve for what our a value out front is, we can plug in 0 for x and know that the output value would be -400 because that is our y-intercept. So what we can do from here then is start simplifying. We have -400 equals a, 0 plus 4 is 4, squared is 16. 0 minus 2 is -2, squared is 4. Sorry, I realize at this point that this actually, I had the wrong value for our 0 here. This is actually at 5. So when we plug this in, this should be plus 5. Sorry, I had the point wrong there. So this is actually going to be 25. And as we simplify, this makes a little more sense. We have 4 times 25, which is 100, divide over the 100. This time we have -4 as our leading coefficient, which again makes sense since this is opening downwards. So our final function this time, -4 is that leading coefficient, x plus 5, quantity squared, and x minus 2, quantity squared. Now the last one then on this page is for you to try. You are writing the equation for that polynomial. Now on the next page, we are going to deal a little bit more with our properties of factoring. Now this time we are going to focus a lot of our attention on our complex numbers. So a reminder, whenever you have a complex zero, a plus bi as a real root, then its conjugate, a minus bi, is also going to be a root. So AKA all of our imaginaries have a buddy. So if I know that 3i is one of my zeros, I automatically know negative 3i has to be my zero as well. Or if 1 plus 2i is a 0, I know 1 minus 2i is a 0. Their conjugates are always buddies. So a lot of times when we're dealing with these complex, all right, we know that we are dealing with square rooting a negative number because we know that we will involve a positive or negative I in our solution. We also can have irrational roots, real and imaginary, so we'll be dealing with a lot of those in these examples as well. So this time we want to factor and find all of our zeros, whether they be real or complex, and we want to make sure that we write our final answer as complete factorizations. So each time we are trying to solve for our x value, and what we notice on this particular one is that when we square root, we have the square root of positive or negative square root 12. 12 can be broken down to be the perfect square of 4 times 3. And we know the square root of 4 is 2, and then the square root of 3 would have to stay inside the radical because it did not have a buddy to move out with. So when we write our answer then in factored form, we have 2 zeros this time. Positive 2 square root 3 and negative 2 square root 3 would be our factored form of that answer. In the next one, when we set that equal to 0 and we subtract over the 6, this time we are taking the square root of a negative number, which means that it will result in an imaginary solution because that negative needs to move out as an I. Now this time, 6 breaks down to be 3 and 2, neither of which are perfect squares, so we would just leave plus or minus I square root 6 as our zeros, and then writing that in factored form, we have x plus I square root 6 and x minus I square root 6. On the next example, it's tempting to just set this equal to 0 and try to fourth root, but really what is happening is this is a difference of 2 squares. So when we factor, what we're going to notice is that we can say, okay, x squared squared is x to the 4th, 25 squared is 625. So our a and our b values this time are x squared plus 25 and x squared minus 25. These then are what we're going to want to set equal to 0. So subtract over the 25, we end up square rooting a negative, so positive or negative 5i become our zeros for that first part. And then the second part, when we add over and square root, we have positive or negative 5 that are real as our solutions. So then in the totally factored form, we have x plus 5i, x minus 5i, x plus 5, and x minus 5 as those complex linear factors, that factored form. Try number 7 on your own. All right, moving down to number 8, we have some factoring where we notice our leading coefficient here is not just a 1 x to the 4th. And we've talked about before that when you have this x to the 4th my x squared constant situation, a, b, c, we can treat this like a normal quadratic. All that will change is that when it's in its factored form, it will be an x squared as opposed to just an x in the parentheses, right? So when we actually start solving this, again, we're going to start like our normal x squared x constant. And we're going to multiply a times c. So 2 times -4 is -8, adds to be our b value in the middle of -7. We get this time that would be -8 and +1. And again, because of this leading coefficient here being anything other than 1, we would have 2x to the 4th, and then this time minus 8x squared, since that was squared, plus 1x squared, and then minus 4. So we're essentially just breaking apart this middle term to be -8 plus 1 as opposed to just -7. From here we group, right? Take out a 2x squared. We have x squared minus 4. And then the second group, we can only take out just a 1. But we see both of these are x squared minus 4, which is a factor. And then 2x squared plus 1, which is also a factor. Last but not least on these, we are going to set each piece equal to 0. This time we are square rooting a positive, so we get plus or minus 2. The second part, when we subtract over the 1 and divide by 2, we realize we're square rooting a negative. So we would have plus or minus I in front of that square root to get rid of the negative. And you could either leave your answer like that, or we can finish square rooting this, and you would also possibly see this as the square root of 1 over square root of 2, which oftentimes they like to rationalize to be square root of 2 over 2. Again, I'm okay if you leave it like this piece here with your zeros. And again, factored form of that then would be that we would take each of those pieces, x plus 2 and x minus 2, and they're being multiplied by positive I square root 1/2 and negative I square root 1/2. All right, last one like this then. We want to be careful because notice again this leading coefficient out front and the 9, we're treating it again like we have just x squared and x. When we add these together then, we are looking for them to equal 145. This actually just ends up being 144 times 1 to get that 144 and add to be 145. So 16x to the 4th plus 144x squared plus 1x squared plus 9. And from here, we want to group. We are taking out a 16x squared, so that we're left with x squared plus 9, and then x squared plus 9 in their second group. Now, the problem with this particular one is that officially all of our answers then end up being imaginary, right? We subtract over the 9 and square root, we get positive or negative 3i. And then when we set 16x squared minus 1 equal to 0, this time we're square rooting the 1/16. And what we notice on this one is, again, if you break this down, square root of 1 over square root of 16, this time it can actually, square root of 1 is just 1, square root of 16 is 4, so it's like we could break this down and actually get a whole number fraction as opposed to needing a radical 1/4 I. And again, positive or negative on that officially as our answers. So when we write our final linear product here, x plus 3i, x minus 3i, x plus 1/4 I, x minus 1/4 I. All right, now one last piece to this. What happens if we cannot factor? Well, sometimes we just need the quadratic formula to be able to solve. So for instance, on this first one, we are able to take out a 5x squared so that we're left with x squared plus x plus 6. However, there is nothing that's going to multiply to be 6 that adds to be 1. That's not possible. So that's where the quadratic formula comes into play, because we have an a value of 1, a b value of 1, and a c value of 6 this time. And we could take x equals negative b, so negative 1, plus or minus the square root of b squared minus 4 times a times c, all over 2a. And essentially what is happening here then is when we simplify, we end up with negative 1 plus or minus the square root of negative 23 over 2, which we know that negative 23 can become I square root 23 and then all over 2. So these would be two of our zeros for our polynomial, the plus and then the minus. Now don't forget as well over here, officially we need to set 5x squared also equal to 0 so that our x value this time ends up being 0. These are both factors, so we officially have 3 zeros on that one. And our final example, again, there is nothing that's going to multiply to be 10 that adds to be negative 3, unfortunately. So we would have to use our quadratic formula where a is 1, b is negative 3, c is 10 this time. And we would say x equals negative 3, right? Negative b, so it's now positive, plus or minus the square root of b squared minus 4 times a times c, all over 2a. And what's happening on this particular one is when you type that piece in underneath the radical, please make sure you are using parentheses around the piece you are squaring, because otherwise you will not get the correct answer for that piece under the radical, which this time is negative 31. And again, we are able to this time move out that I and get square root of 31, just that piece. So both of these would be imaginary zeros. 3 plus I square root 31 divided by 2, or 3 minus I square root 31 over 2. Thanks everyone for watching. We'll work more with these in class.